Okay, good afternoon. Let's wrap up our theory of semiconductors today. From next week onwards, we'll zoom out. We won't look at the atomic structure anymore or subatomic particles, nothing of that sort. We'll look at the components and the circuits that we'll analyze using those components. Okay, so today is the last class on semiconductor theory. So let's bring up the class notebook. All right, so we stopped at, let's see, electrical conduction and semiconductors. And in this class, we are going to take the P and N type material. We're going to join them together. So far we learned that we have intrinsic semiconductors that have certain amount of charge carriers present inherently or intrinsically due to thermal energy. Then we introduce external electrons or holes by adding impurity dopants to our semiconductor material. And because of that, the number of charge carriers are now in such sufficient numbers that we can control the flow of these charge carriers. But overall, electrically speaking, no matter what type of semiconductor we have, electrically speaking, it is charge neutral, right? So we have a P-type material, we have an N-type material. By itself, it's not of much use except in a few certain applications. But the real magic happens when we bring two dissimilar semiconductors together, meaning if you have a P-type material created in silicon and an N-type material created in silicon, what happens when both of these come in contact? Okay, so first thing that comes to mind is if it's a metal, it'll have conducting capabilities, but real life conductors will have some resistance, right? So we can model it as a resistor, meaning the relationship between a voltage and the current would be linear. So similarly, if it's a doped semiconductor, we have now introduced many charge carriers in there. It's not quite metallic, not even metal-like, but it should be able to conduct, right? So if we apply a voltage, we should have a proportional current flowing through it. That's the theory. That's what we would expect. So if we connect P and N junction together, we would think that the voltage and current relationship would be linear. But when they first perform experiments, it turned out that's not what they received. I mean, that's not what they discovered. What they actually discovered was this, a very non-linear relationship. Okay, a very non-linear relationship. So as the voltage was increased, meaning it was turned more positive, there was no conduction, there was no current until a certain level was reached. That voltage level is breached and then exponentially increased the current. So completely non-linear. Hence, we say these are non-linear devices because the relationship between the voltage and the current is not linear. Okay, so it's non-linear response, hence a non-linear device. So far, so good, right? They also discovered that if you decrease the voltage, meaning you apply negative voltage, then there was no current flow for a very long time. Not time, sorry. For a long stretch of, for a long range of applied voltage. So this is not to scale, obviously. This is not to scale. There are no values on it. So we discuss the positive. This is the negative. Negative side, voltage keeps on increasing, but nothing happens. And at some point, you have a large increase. So no current flow in a almost linear relationship, not linear, sorry. I need some coffee. Almost linear slope where current increases dramatically. Okay, that happens when you apply a negative voltage to the same PN junction. So let's look at what is happening at the subatomic level. Okay. So here we have a P-type material, you have an N-type material. Standard dots represent electrons, circles represent holes. You have excess of electrons in the N-type material. You have excess of holes in the P-type material. Now, electrically, of course, it's charge neutral. You bring them together. What's going to happen when electrons come in close proximity with holes? Attraction, and then it jumps into that spot. Some of them will recombine. When recombination occurs, charges will disappear. So the first thing that happens is when you bring these two dissimilar semiconductor types into contact, remember we spoke about diffusion. So there's a charge imbalance. There's a charge imbalance. We have P-type, meaning a lot of positive charges on the left side and a lot of negative charges on the right side. So there's a charge imbalance on either side of the junction. So the charges will start to diffuse through the junction in a bid to even out the charge. Okay, so diffusion takes place. This is known as the junction. Okay, this is the junction. So that junction is the border between the P-type and the N-type material. Because there is a gradient in the charges will start to diffuse through the junction on either side. Holes will move over to the N side, electrons will move over to the P side. And then when they come into close proximity, recombination occurs. So recombination is right here. And the charges disappear, right? Electron falls into a hole, one negative charge and one positive charge goes away. So charges disappear. But what is left behind are the ionized atoms because they are immobile, right? We have these squares that represent the ionized atoms, donor atoms in the N-type and acceptor atoms or acceptor ions on the P side. So they are ionized, they have charge. Now they lost their electron, they lost their hole, but they are left behind with one extra charge. So donor atoms will now have one fixed positive charge, and acceptor atoms or acceptor ions will have one fixed negative charge. Let's take a pause while you think over that. Let me know if you have any questions. So far, so good. You all with me so far? Okay. So again, holes and electrons cross over, recombine, charges disappear, meaning the free moving charges disappear, but there are fixed charges due to the ionized atoms on both sides. So on the N side, we have positive charges, and on the P side of the junction, you have buildup of negative charges. When you have positive charges on one side and the other dissimilar charge on the other side, causes an electric field. And because there's an electric field, it opposes the flow of further majority carriers. Okay. Again, charges are left behind, and these uncovered fixed charges give rise to an electric field, and that electric field is going to oppose any further diffusion of the majority carriers from either side. Meaning this electric field is going to prevent the holes from going towards the right, and it's going to prevent the electrons from going over the to the left. So the reason that happens is because the hole must move against the field. Holes, positive charges, they love to move with the field. So in this, the field is going from left to right. Sorry, right to left. Okay. Right to left. Because you have positive charges on the right, negative on the left. So electric field is pointing in this direction, always from high to low. So if it's flowing in that direction, there are negative charges. If the majority carriers now want to cross the junction, they must work against the field. Same thing with the electrons. The electron must move with the field, but their natural inherent ability is the exact opposite. Hence, the electric field stops further diffusion of these charges. And so there is a point in this reaction where everything comes to a stop. And that's what was discovered. And then once they discovered this, they performed experiments and they came up with a conclusion, postulated the theory of what is actually happening when you bring a P and N side material together. One more thing before we take a pause. Right here, the electric field is not zero, it's not neutral, but there is no free moving charges in this region. Okay, so this region is known as the space charge region. Space charge region. SCR, some books stick with SCRs, but more commonly, this region is known as the depletion region. So again, in semiconductor fabrication, device physics, semiconductor devices, this region is always commonly referred to as the depletion region. The reason being that this region right here is completely depleted of all free charge carriers. Okay, so now let's take a pause, think over that. Let me know if you have questions. Any questions? Did it all make sense so far? It's not an easy topic to grasp within a few minutes. So again, it requires reading and understanding outside of class time, as with any other classes that you are taking. Okay. Okay. All right. So the junction is actually preventing the majority carriers from crossing over. Remember the goal. The goal is to create a device that can current conduct through itself, right? If you have holes in the P side and electrons in the N side, they should move across the junction. When they move through the device, that's when we can say the device is conducting. The device is conducting current. So the goal is to get the holes to cross over from the left and the electrons to cross over from the right, right? That's the goal. But the built-in barrier stops that from occurring, which is actually a good thing. Because if that reaction is allowed to progress unimpeded, then the charges will just even out throughout the entire structure. Yes. So the question being asked is this why Moore's law broke down? Yes, no, kind of. Moore's law is not a law, actually. He's not the one who actually coined it. I mean, he observed. I like to call it more like a theorem, because a law, by its very sense, is inviolable. And especially if you're talking about something related to physics, then it's occurring in nature. It's not something we can change. So I like to call it like Moore's prediction rather than like law. Moore's prediction, Moore's theorem. So Moore's theorem was early on when they were building these devices on integrated circuits. He discovered, or he noticed and observed, that the number of transistors that are built in a microchip were doubling every 24 months. Okay, every 24 months. So that was the early days of semiconductor industry being set up. And so that has more or less proven true all the way over the past few decades. But now, as pointed out, that moves, we are approaching the limits, and the number of transistors is not quite doubling every 2 years. So because we are creating feature sizes smaller and smaller and smaller, so one aspect is yes, but it's not just the depletion, it's just the overall structure is so small that we cannot fabricate it by normal, so you have to find like very roundabout ways of fabricating these devices. Even with that, we are approaching the atomic level in terms of like fabrication. So it's pretty incredible, yeah. So as I was saying, the electrons love to travel against the field. Holes want to travel with the field, right? And that's the reason why that built-in electric field is opposing the movement of these carriers. So if these carriers cannot cross the junction, there's no current flow. So as it is, if you create a PN junction device and you just sit it on the table, nothing's going to happen, which is actually a good thing because we want to control the flow of current, right? So again, the junction favors the minority carriers and it discriminates against the majority carriers. And the reason is, of course, this. So electrons go against the field and holes go with the field. So now, if you are an electron in a p-type material, you're free to move with the field. And if you're a hole in the n side of the n-type material, you're moving with the field. So the minority carriers on both sides in both semiconductor materials are free to cross the junction. Okay. And when they cross the junction, there is a very, very, very minuscule current that flows because obviously minority carriers are very small in number compared to the majority carriers. Okay. So that current is known as the drift current because it's drifting in response to an electric field. So those minority carriers find it very easy to cross that barrier. But again, it's typically very low because the low number of minority carriers. Okay. All right, 130. So relative dimensions. Every hole that is lost and every electron that is lost to the recombination process leaves behind one negative ion and one positive ion. Uncovered simply means there is a charge left. It's not balanced or covered by opposite charge. If you have an ionized positive atom, it is balanced by a negative electron. It's an ionized positive atom. If it's ionized negative atom, then you have a positive hole that is associated with it to keep it neutral. But because they are lost to recombination, every hole and electron lost is creating two charges, one on either side. So depending on the concentration, right here, depending on the concentration of the impurity dopant, the junction could be larger or smaller on either side. Okay, larger or smaller on either side. So again, remember, by its very nature, the phenomena is trying to do what it is trying to do is it's going to balance out until it is electrically neutral. Okay, until it's electrically neutral. So the total number of charge on both sides of the junction must be exactly the same. So if there's a higher doping concentration on one side and a lower doping concentration on the other side, if you want the charge density to equal, then that means that the lower density must occupy a larger space, and the higher concentration charge should occupy a smaller space. Does that make sense? Again, I'll repeat. The point of this phenomenon is that it should, not it should, it will result in an electrically neutral junction, electrically neutral PN material. In order for that to occur, the only explanation is that if you have concentration of electrons that are higher in the N side and concentration of holes that is lower on the P side, for both sides of the depletion region to be electrically balanced, meaning the charge density should be the same, the only way that can happen is if charges are higher on this side, the area would be smaller. And if charges are lower on the P side, then the area would be bigger. That's the only way the charge densities would equal and cancel out. And so if you have a PN material with a higher concentration on the N side, so here's just a example where Nd is 3 raised to 16 atoms per centimeter cube. On the P side, it's 1 into 10 raised to 16 atoms per centimeter cube. So the number of electrons or the donor atoms is 3 times as much as the number of acceptor atoms. And so the ratio of this concentration will be equal to the ratio of the junction width on both sides of the junction. Okay, so the junction is right here in the center. That's the junction. Xn is how far into the junction. So it's the distance. X is the distance as measured from the middle of that junction. The junction point is 0. Xn and Xp is how far into the material the diffusion occurs, the space charge region occurs. Okay. So if N has a higher concentration, then Xn will be lower than Xp. So you can see here, Xp is 3 times Xn. So the ratio must be the same. Okay, the ratio of the distance on either side of the junction is the same as the ratio of the doping profile. Okay. All right. So just a few graphs to explain a few more things. Excuse me. So the depletion region width is given by this quantity WD0. It's a lowercase w. Lowercase w is also used for anyone? Energy. Lowercase w is also used for energy. Uppercase w, power, watts, named for James Watt. Okay, so WD0, D, of course, is the depletion regions or the width of the depletion region. And then the equation for that is given here. All right, so if you take the area under the curve, charge density, that would equal or cancel each other out. Okay. Higher the concentration, the narrower the distance, and the lower the concentration, larger the distance. So this is the junction. I like to say this is 0. This is 0. And then this is how far it extends into. This is Xn on this direction and Xp. Actually, This is Xn, and this is Xp. Okay. All right. So this charge density gives rise to an electric field. Obviously, there are mathematical. We integrate the entire area, and we can obtain the electric field as shown here. It's labeled as E max, the max of the electric field. But more importantly, this E max gives rise to a voltage, or we can measure the quantity of this electric field as a voltage, and we refer to it as the built-in junction potential. Built-in junction potential, hence VBI. VBI. So in this course, this book referred to as VBI. Some e-books, different authors like to use their different terms. I've also seen this referred to as phi J. Phi is the Greek letter phi, and then J for the junction. Okay, but VBI is the built-in junction potential, and this junction potential is near constant for every semiconductor material. So it's a material property, and it stays constant across all kinds of doping profiles. For silicon, it's approximately 0.6 to 0.7 volts. For germanium, it's about 0.2 to 0.3 volts. Gallium arsenide, gallium phosphide is slightly greater than 1.1 and 1.5, depending on the doping, concentration in the profile. Okay. So this is the voltage that is required to overcome the junction barrier and allow current to flow through the device. Okay. Okay. So the equation for VBI shows us that it depends on the doping concentration, right? Na or Na times Nd, but divided by Ni square. Okay. So there are slight variations, but typically for every single material, it'll be within a specific range. So all silicon diodes, depending on the construction, pure silicon diodes will always have a junction potential that is close to that number. Okay. All right. So you have a PN junction. It's an example with the given doping concentrations, Na and Nd are given. You're asked to calculate the built-in junction potential, the junction width, and the built-in electric field, Emax. All three of them have standard equations. Okay, so VBI is here. And then WD0. Yeah. Let's just do it this way. Okay. And then let's see. All right, that'll work. All right, so standard equations, all you have to do is plug and solve. If you look at Emax, it requires VBI and WD. So we save that for the last. Okay. Then we first find VBI. VBI requires NAND. NAND is given. So we simply plug that into the equation. But we need Ni square. So what value can you use for Ni square? Right? That's 9.2, 10 raised to 9. Want to keep it simpler, we can just assume 10 raised to 10 atoms per centimeter cube. Okay. Now, This is rather straightforward because there's an equation you simply plug in. So what I'm going to point out, the common errors that occur while we're trying to calculate these. Okay. So NA and ND, right now this is not shown, but it's atoms per centimeter cube. Okay, atoms per centimeter cube. So atoms per centimeter cube. Then when you plug it in here, Ni square will also be in centimeter cube. Okay, but it's Ni square. It's 10 raised to, it's per 10 raised to 3. So 10 raised to minus 3 times 10 raised to minus 3. Okay, Ni square. So you have to be careful that you resolve all units and all unit prefixes. I always like to resolve it all the way down to meters. So if it's micron, I'll convert it by 10 raised to minus 6. If it's centimeters, 10 raised to minus 2 or 10 raised to 2. Okay. So be careful when you plug those values in. Then the third quantity is, or the fourth quantity is VT, thermal voltage. Thermal voltage, last class I pointed out, is KT over Q. At room temperature, if you take T as 27 degrees C, you can take T as 300 Kelvin. So 300 Kelvin, and that is accepted as room temperature. Okay, even though 27 is quite higher than what we'd expect to see here. Okay, so we'll say room temperature is 300K. You calculate that. It turns out it's about 25.8 millivolts. So 300K, VT is 25.8. Many books and authors like to use 25.9. There are also some books out there that I've seen. They simply like to use 26. Okay. But if you're performing a calculation, do not use 26. So I'm going to write it right now. Do not use 26 millivolts. Okay. Always calculate. So always calculate using this. K is the Boltzmann's constant. Pretty standard. Q is the standard unit charge. Plug those values in, and you should be able to get 25.8. I typically like to go 3 or 4 decimal places. So you plug those in, you find VBI. And once you have VBI, you can plug it into the equation for WD. WD has the same NA, ND, and VBI. We have epsilon R and epsilon 0. Anyone familiar with these? Should be from capacitance. Do you study capacitors in 115 or 215? 215, okay. So, all right, quick recap. Anyone remember the equation for capacitance? Epsilon A over D. Okay, the epsilon is epsilon 0, it's epsilon R, A over D. A is a cross-sectional area of the 2 plates of the capacitor. D is the distance between the 2 between the 2 plates. Okay, and epsilon 0 and epsilon R refer to permittivity. So in this case, the Greek letter epsilon is referring to permittivity. And that permittivity has to do with the insulating material that is used. Okay, so it's a material property. So epsilon refers to permittivity. Epsilon 0 is permittivity of free space or vacuum. So that's a constant that is given here. Or vacuum. And this is the relative permittivity of the insulating material. Relative permittivity of the material, but it's relative It's relative to epsilon 0. So it's a ratio. Okay. So epsilon 0 has units of farads per meter, but epsilon r is a ratio. Hence, it's dimensionless. Okay. So here we are assuming, in this example, it's a silicon material. So epsilon r for silicon is 11.7. Epsilon 0 is a constant, so 8.85, 10 raised to minus 12 farads per meter. This is given in centimeters. Again, I don't like when they use units like these. Always prefer to go standard so that I don't make any errors in calculations. So 8.85 10 raised to minus 14 farads per centimeter, but it's 8.85 10 raised to minus 12 farads per meter. Okay, convert that to meters, Na, Nd to meters, and when we calculate VB, I also convert everything to meters. That way I don't have to worry about any errors. And then Q is the standard unit charge. Calculate, perform your calculations. You get values for VBI, WD. Plug that into the equation for Emax, and you calculate the energy that's developed in there. So all you need to know is the doping concentration and the type of material that is being used, and you can calculate everything. All right, let's take a pause. Think over that. Let me know if you have questions. Yeah. That's pretty standard for silicon. So that's, again, is a constant that depends on, it's a well-established number. Sometimes I, just to make it easier, I just take it 10 is to 10. So 9.29 is very close. So if I'm going to rush, I'll just take 10 is to 10. But at 300 Kelvin, the intrinsic carriers that are generated are about 9 times 10 is to 9. Again, that's different for every semiconductor material. So one of the previous slides, there was a chart that described how many, there's a chart of the number of atoms, charge carriers that are generated as a function of temperature. Did that make sense? Okay. All right, 148. Let's see. How many do I have? Modulation. Got 4 or 5 slides. Okay. All right. So this is what's happening. You have the junction. It's completely devoid of charges. It's electrically neutral. It's balanced, right? There's nothing happening. In order for the device to conduct current, the carriers, the majority carriers, must cross the junction. If they're not crossing the junction, then there's no current flow in the device. So when when you connect these, we can describe that potential. This graph right here, right? So these are the holes on the left side, and these are the electrons on the right side. Okay, and the electric field is going from this side to this side, right? Positive to negative. So that's the electric field, right? So the electric field is going from negative to positive, and that is indicated by this graph right here. So the holes, as we stated earlier, the holes must go against the electric field, and the electrons must go with the electric field, which is the exact opposite of their inherent property. Okay, so they are both working against the electric field in a sense. Okay, in the previous 2 slides, I stated holes would like to move with, and electrons would like to move against, but it's the exact opposite when the majority carriers come. So there's this built-in barrier. The holes need energy to go to the other side. The electrons also need energy to cross over the junction. So what happens? Well, we provide external energy, external electric field, meaning in simple terms, you're applying a voltage. If you apply a voltage, I'm assuming everyone at this point is familiar with the symbol of a diode. What do these stand for? Anode and cathode. That's what they used to call them, A and K. Now I think some authors have started just referring to them A and C. But again, C is for capacitance, it's for coulombs. And so that convention K has been carried over from the vacuum tubes, okay, anode and cathode. So if you have a diode, it's a triangle pointing in one direction, it's an arrowhead. It points the direction of the current flow, okay? And the straight line or the bar that you see, that's the cathode, okay? So if you apply positive, so this is the P side and this is the N side. If you apply a positive voltage or polarity to the P side and negative to the N side, we say this is in forward mode. The application of the external voltage is also referred to as biasing the device or biasing the circuit. Hence, this mode is known as forward bias. Forward bias. And if you apply negative and positive to P and N side respectively, we get what is known as reverse bias. Yes. And the Schottky diode is different. We'll talk about it later. Let's get done with this. If you increase the magnetic carriers, you'd have, what did you say? Larger reverse current. Not just magnetic carriers. So if you have a, it depends on the doping. So if you have a lot of dopant concentrations, we can increase the current. It all depends on the amount of doping we introduce. Okay, so the question being asked was in the reverse bias, what happens when you have a whole lot more atoms? But we'll table that for a little bit later. Okay, so what exactly is happening? We have, actually, you know what? Let's go to this graph. This makes it easier to actually describe this. All right. We got electrons on the N side. We got holes on the P side. If you apply negative on this side and positive on this side, what happens? Positive to the P type. Holes are positively charged. Electrons are negatively charged. If you apply a negative polarity to the N side, what happens to the electrons? It's going to go that way because you're pushing the electrons. Again, you're working against the barrier, but you're imparting, if you apply just 0.1 volt, 0.2 volt, 0.3 volt, the electrons not acquire sufficient energy to cross over. But for silicon, for instance, as you start crossing 0.5, 0.6, 0.7, they acquire sufficient energy, so they are overcoming the barrier, the junction barrier, and they're crossing over the junction. The same thing happens here. Positive polarity is going to push the holes through the barrier. So barrier effectively, it does not actually shrink, but effectively we can say the barrier kind of shrinks. But it's not actually shrinking because that 0.6, 0.7 volts will always remain there. We are simply imparting sufficient energy to the holes and electrons to cross over. Hold the questions I pointed out. And at the same time, not same time, if we apply negative here and positive here, what happens? So they're attracted, right? So they're going to pull away. If they're getting pulled away, that barrier is effectively being increased. So that's known as reverse bias. So let's take a pause, think over that. Let me know if you have questions. Yes. Sorry, I like to keep my hand like this. If anybody asks for that, I don't forget. Yes, that's what it is. Yep. That's not just silicon, all diodes. All semiconductor diodes this this phenomenon occurs. Okay. Yes. Yeah, that's called the metal semiconductor diode. It's one of the ways Schottky diodes are manufactured. Metal semiconductor junction. So the point was about like a metal semiconductor junction. Those are special kind of diodes. One of the Schottky diodes, right? That we already used in the lab. And so one side is a metal, the other side is a semiconductor, specific type of semiconductor. And so the metal acts, well, not acts, but it has plenty of free electrons, right? There's plenty of free electrons. So the barrier, excuse me, the barrier that is established at the junction is very small. And so the lab experiment you performed, which used BAT54, had a barrier of what, 0.3, 0.35 volts, right? Far lower than what silicon diodes. And the movement is very fast. Okay, so it's much faster speeds than a regular silicon diode. Okay, so a couple of minutes left. So again, let's go back here. So forward bias effectively lowers the junction barrier, but it's not actually lowering it because that voltage remains fixed. It's simply imparting sufficient energy so that they can overcome the junction barrier and cross over. Okay, hence we get the characteristic curve that looks like this. You know, until 0.6 volts, not much current flow, then there's a sharp curve and it goes upwards. So for a small increase in voltage, a huge increase in the current. Okay, that's why we have these kind of characteristics, VI. And reverse bias, the exact opposite happens. The junction barrier is now increasing in width because the electrons and holes are pulled away from the junction. So if that's happening, the only thing that flows across are the minority carriers because they're the opposite polarity, right? So the minority carriers are the only ones that are going to flow across, and the minority carriers are fixed in number. They are very small in number, and so the current that flows is very, very low. Typically, it's on the order of nanoamps and picoamps. Okay, 10⁹, 10⁻², 10⁻15, very, very small. So reverse bias, the reverse current is due to minority carriers, approximately 10⁻⁻9 to 10⁻15. All right, VI characteristic of an ideal diode. So we just have about a minute left. If you have to leave, you're free to leave at 2 o'clock. I'm just going to continue on until I finished all 3 slides. Okay. And there are some additional reading slides at the end. So if students want to take their understanding a bit further, you can go outside the syllabus and look at those slides at the end. So the equation for the diode is given here. This is known as the diode equation. Is also known as the Shockley equation after William Shockley, as one of the inventors credited with the invention of the solid state transistor. Okay. So Shockley equation, diode equation. So it basically is saturation current IS e raised to VD or NVT -1, but then 1 is pretty much we ignore it. So N is an ideality factor. Typically for typical diodes is just 1. So we ignore that too. Thermal voltage VT right here. That's pretty standard for at any temperature. So the relationship typically breaks down to diode current ID is equal to IS, the saturation current, E raised to VD over VT. That's it. And it's a good approximation. So even though we ignore many of the quantities, this is a good approximation. Okay. So diode current is proportional to the exponent of the voltage that you apply. So this is the relationship between the diode voltage and the diode current. IS is a constant. It is defined and given in the manufacturer's spreadsheet, spec sheet or the data sheet. So every diode that you looked up the BAT 54, it'll have a value for the reverse saturation current or IS. Okay, so any diode spec sheet that you look up will have a value for IS. Okay, IS for the most part, we consider it to be 0 in the negative or the reverse bias. This is minus V, this is plus V, plus I, minus I. So that's the VI characteristic of an ideal junction diode. The last one, that's the saturation current, IS, of the junction diode, depends on the doping profile of the semiconductor material. So depends only on the minority carriers, right? Only on the minority carriers. So it depends on ND and NA. So this equation, again, I just like to show this, but I'm not going to assess students on any of these equations. Okay, just to show that the dependence of the saturation current is only on the minority carriers. Okay, but of course, everything is affected by the doping profile ND and NA. D is the diffusion constant, how far it's diffusing into the junction. There was previous slide in last class where I didn't go over it in class, but it's there for students to take a look at. If you have any questions, you let me know. All right. So again, IS, sorry, when you apply reverse bias, the only current that's flowing is the reverse saturation current, and that does not change with voltage at all because the number of minority carriers remains exactly the same. If it passes a certain point, the junction breaks down and heavy current starts to flow. But that's a discussion for another day. Okay, so we'll end class here today. I will pick up again on Monday. There's an assigned reading, but it deals with large signal models for the diode, so it's not needed. But we'll have a quiz on Monday that will be covering the material that we learned in the previous 3 classes. Okay, yes. No, not today. If there was, I would have announced it by Wednesday or even before than that. And then after this, there's some additional reading if you would like to do. There are a few slides about mobility and a few more equations, right? So, all right, let's stop here.